Introduce our speaker. Thank you, Mary.
All right, we have Mike Oard today. He has a BA and an MS in atmospheric science from the University of Washington. He has worked in atmospheric research and retired from the U.S. National Weather Service after 30 years of service. Michael has worked in creation research in earth sciences for about 50 years and is an author, co-author, editor of many creation science books on the Ice Age, the Flood, geology, and weather. He has also published hundreds of research articles in creation science literature. He is a fellow of Creation Research Society. Michael has been married for 55 years and has 4 grown children, 12 grandchildren, and 2 great-grandchildren. His website is michael.ords.net with 2 free ebooks. Let's welcome Mike Oard.
Well, good morning from Montana. Glad to be here again. It's a privilege to be here. I think this might be my 15th talk or something of that sort. Anyway, that website is actually michael.j.ords, O-A-R-D-S .com or net. I don't call it up from memory. I just hit a button. So anyway, this talk is going to be about sediments or sedimentary rocks. There's sedimentary rocks on the continents, but there's sediments in the ocean. But I'm just going to call them all sediments. And this is part 2. I talked about this subject 2 years ago, so some of this will be a review, if anyone remembers that. It's very difficult to remember what I read even a month ago, so I take notes and have to read things again. But anyway, this is an update of our project. There's 4 of us involved. We've been doing this for 6 years, trying to figure out where the sediments are and what they mean. The flood's all about sediments, eroding them, moving them, and depositing them. So where'd they go? Where'd they come from? Also reveal a lot about the flood. We wanted to develop a sophisticated flood model because in the earth sciences, we have hundreds of challenges to answer. We have a lot of answers, but we still have several hundred. Why do we have several hundred? Well, mainly because we don't have enough researchers to do it. And secondly, some of these questions take years, tens of years to answer. But if you have a sophisticated flood model, you can use that to answer the other questions. And it can help determine the flood boundaries. There's a big controversy over where the top flood boundary is, flood post-flood boundary, and the flood pre-flood boundary. And by determining the upper boundary, we can determine what happens after the flood, when people are spreading over the earth, animals are spreading. Did they have to dodge huge tectonics, huge landslides? And we want to know those things. And so do a lot of people that are looking for answers from us. They want to know too. So in this project, we divided it up into just the oceans and the continents. The reason we did that is because the secular scientists have this great research project on the ocean sediments, which I will get into. And we're going to only deal with the bulk sediments. Sediments or sedimentary rocks themselves, we don't care about where they line up in the geological column or the ages. And we have no regard for megasequences, just talking about sediments, where they came from, how eroded, things like that. So far, we've determined that sediments eroded, the amount of sediments that eroded from the continent during the retreating stage, when the waters are running off the continents as the continents are coming up out of the floodwaters and the ocean basin sinking, causing a powerful currents to flow off. We also determined the sediments or sedimentary rocks left over from about 2/3 of the United States. We're going state by state because we tap into the state geological surveys, and they have seismic data, they have maps. They have well data. In Kansas, we got thousands of oil well data. So we have a pretty good feel for the sediments in Kansas. We've discovered some amazing features below the sediments on top of the continental crust. The continental crust is mainly granite at the top and some metamorphic rocks. Also, we've transitioned, and this will be new stuff mainly, into a model for the origin of the Appalachians, which is very difficult. I will get into that. Okay, future goals. We want to find out where the sediments originated before the flood. I've had various ideas. I, at one time, believed that they maybe came from the Pacific Ocean, because the sedimentary rocks are on the continents, but not in the ocean. So it would imply the continents were lower and the oceans were higher, and the sediments were deposited on the continents from the ocean. That's what I thought at one time, but I've since changed my mind. You got to be open to change your mind in creation research. And I changed my mind about several things lately. Also, we want to determine the mechanisms of early flood erosion. Okay, some results. This will mostly be a review for those that can remember precisely what I said, but I doubt whether anyone does. I don't. We've determined the sediments eroded from the continents during the retreating stage. So here's this little diagram I like to use. You can divide the Genesis flood up into two stages, just like any flood. The water rises and the water subsides. So it's a flooding stage and a retreating stage. But from the Bible, you can determine 5 phases. Phase 1 is probably, we think, the first 40 days, because that seemed like that's where all the heavy rain occurred. The heavy rain decreased after day 40, and the fountains and the windows were closed, and the ark runs aground on day 150, which we believe is the peak of the flood. Between day 41 and day 50, we have a gradual rise, like Henry Morris and John Whitman call it the prevailing of the flood. We have a lot of catastrophism early, and then it sort of settles down and it prevails until a maximum. Then it runs off. It runs off when the mountains and the continents come up out of the floodwaters and the ocean basin sinks. And as it's running off first as wide currents, and then as more mountains and plateaus are exposed above the floodwaters, it's forced to channelize the floodwaters. And in both of those phases, phase 4 and phase 5, you erode the land in certain ways that we can detect. So here's kind of the big picture, wide currents, like that. And then as the mountains uplifted, the water will continue going east, and then they'll have a backwash going to the Pacific Ocean. And this is in the western U.S. This is big scale, by the way, this schematic. And some of the erosion of the continents are greatly eroded. Like here's the Grand Canyon to the very right there. And to the north, we have the Grand Staircase. How many people have been to the Grand Staircase? Quite a few. So you know generally what I'm talking about. The resistant rocks become your cliffs, and the soft rocks are eroded back. So you form five or six stairs. 5. Anyway, when you add up that, it's dipping to the north about 5 degrees to 10 degrees. This is greatly exaggerated, this diagram. So that's about 10,000 feet of sedimentary rocks that used to be up over the whole Grand Canyon area. Before Grand Canyon eroded, you eroded off 10,000 feet of sedimentary rocks. Here's another schematic of it. You can see Grand Canyon on the right, and you can see those cliffs, and Zion Canyon, same thing. So you erode that massive amount of sediment during the sheet flow stage, the wide current stage. You take off that whole area, and then in the more channelized phase, you erode the canyons, like Grand Canyon and Zion Canyon, which shows up there too. And then after the erosion, it left a rough planation surface, a flat surface generally. And this is looking at the planacian surface around Grand Canyon from Red Mountain. Yeah, my cursor shows up. Grand Canyon is in that area there. You see in the north rim. And the reason you see the north rim there is because Grand Canyon, the Kaibab Plateau, slopes from north to south. And the canyon was cut at intermediate levels, not at the low points, which is a major mystery of secular earth science. So, there's been a huge amount of erosion. So the first order of business is let's find out how much sediment's in the ocean. The secular people have been doing this for years. They've had 3 estimates. The latest was published by Stromy et al. In 2019 in the journal called GQ. That stands for Geochemistry, Geophysics, and Geosystems. It's a journal of the Geophysical Union, American Geophysical Union. The latest estimate, after 3 iterations, increased the sediments by 30%. We think they probably got it pretty close this time because they found sediments in places that were hard to get, like the coast of Antarctica. So here's the results of their research. And notice the color code there. That the yellows are very little sediments, which you find in the middle of the ocean. And as you get down and you get into the blue area, right there, you're up to about 15,000 meters. That is around 50,000 feet thick. And then and it goes deeper than that. So you can see where the sediments are. They're mostly along the edge of the continents. Very key point. For instance, off the east coast here, you have sediments up to 18 kilometers. Let's see, translate into feet, multiply by 3.3, you got almost 60,000 feet of sediments off the east coast. The Gulf of Mexico has a tremendous amount. And surprisingly, in the Arctic Ocean, on the Arctic continental shelf in northwest Canada, you got about 15 kilometers of sediments. Same off of Norway, and the Bay of Bengal, and in Antarctica in the Weddell Sea. That's a lot of sediment. The key is it's close to the continents, and that gives us a hint of where they came from, which I'll get into. There's a little cross-section across the Atlantic, and it's very small scale, but you could see on the left there, you see the continental shelf, and where the sediment's piled up to about 15 kilometers thick, or 15,000 meters, and then hardly anything across the ocean until you get to Africa, almost 15,000 feet too. This line down here is the boundary between the crust and the mantle. It's very thin in the ocean, but it deepens as you get into the continents. Tremendous amount of sediment along the coast. And we've been able to do some mapping and cross-sections of these things. Now, Dr. John Reed, who is a PhD in geology and is expert in the English language, he's the heavy lifter. He does these maps with, I think it's GIS. Anyway, here's the Arctic Ocean, and I'm only going to showcase cross-section AA in the upper right corner there. And you can see the red there. In the red, it's, or the pink, it's around 18,000 meters of sediments. And this is what it looks like when we do a cross-section. Now, this vertical line here is the shoreline. A lot of sediment onshore, but offshore. Look at that huge amount of sediment there off of northwest Canada. Where did that come from? That's the question, which I'll get into. I'll just summarize what I've done before. And this is the cross-section from Antarctica through the Weddell Sea, and you can see it gets into the reddish colors, which are 15,000 meters or so. And that cross-section, called D prime, is like that. Huge amount of sediment along the edges of the continents. Where did it come from? Okay. And let's get to the U.S. I'm only going to show you 2 cross-sections out of 3 possible. One through the Gulf of Mexico. It actually starts in Texas, and goes through the Gulf of Mexico to almost the Yucatan Peninsula. And it looks like there's a lot of water in the Gulf of Mexico, but when you see that cross-section, you'll find out it's mostly just a pile of sediment with a little water. And I'll give a cross-section of HH. And this is the Gulf of Mexico. Here's the shoreline right here. Huge amount of sediment in Texas. Coastal plain sediment, dated mostly Cenozoic, I might add. And here is offshore in the Gulf of Mexico up to over 15,000 meters. And then it goes up towards the Yucatan. So the Gulf of Mexico is mostly sediment and a little bit of water. You wouldn't know that unless you can do seismic data, oil well data. So these are some of our results. Off the East Coast, here's the shoreline right here, cross-section HH. And a lot of sediment onshore. Then we get onshore, you get thick sediments. And still going offshore, you still have a fair amount. And the reason, here's the shoreline, the reason why you don't see the ocean water till here is because this is the continental shelf. And that drop-off's the continental slope. See, along the continents, you have the slope which decreases very slightly going out in the ocean. And then when it gets to about 100 meters, you have a big drop-off called the continental slope. And then it can continue down to the continental rise. So that's some nice cross-section. So the big picture is massive erosion to form the continental margin sediments. Kind of like this. You get uplift of the continents and sinking of the ocean basins. Floodwaters are running off at high speed sometimes. Now this is a cross-section for Southeast Africa that I did. And it forms the continental margin sediments, leaving features like this, including the African surface, which is a giant planation surface over 60% of Africa that's been faulted or folded up to different altitudes, a coastal plain, and thick continental margin sediments. So the continental margin sediments came from the continents. And here's a typical shelf and slope off Los Angeles. And you can see where the continental slope sediments are almost flat, and they decrease very slowly out to about a drop-off called the continental slope. That's typical, and that's a very unique profile, by the way. With present processes of erosion and deposition over millions of years, which is a secular model, you wouldn't expect a profile like this. You'd expect a gradual profile down to the deep sea like this, but you have this. And that's because you had massive flood runoff that formed a huge delta, 1,000 miles wide, all along the East Coast and other places. And other erosion features. The continents have been greatly eroded. Here are some figures from the secular literature. For the Colorado Plateau, an average of 2,500 to 5,000 meters. 5,000 meters is about 17,000 feet. More than 1,600 meters over southern Arizona, 2,000 meters southern Rocky Mountain foothills of Canada, 6,000 Flinders Range, South Australia, 1,000 to 3,000 meters southern Africa. Now, the next two are really important, as I'll get into. 8 to 11,000 meters, the Vredefort impact structure of South Africa. These give us a clue of where the sediments came from, which I will get into. And then another massive impact in southern Ontario, Canada, 5,000 meters of the Sudbury impact structure. And I've done my own calculations in 5 areas. I verified 6,000 meters over the central Appalachians based on the rank of coal and the amount of sediments offshore. 2,400 meters Namibia, Africa, based on the sediments offshore. 1,600 meters southeast England based on the eroded anticlines. In the north limb it's called the North Downs. In the south it's called the South Downs in England. And San Rafael Swell, which is in the northwest Colorado Plateau, 4,200 to 5,100 meters of erosion. And central Montana, where I used to live, about 2,000 meters. And that one was based on the character of sandstone at the surface. because to form sandstone, you have to press it down, you have to chemicals moving through it, and that gives you an idea of how much overburden was above it that got eroded during the retreating stage. So along the way, we're learning all kinds of interesting things about the flood, tectonics and erosion, deposition. This is the San Rafael Swell in the northwest Colorado Plateau. This was done just by trigonometry. The sediments dipped to the north about 8 degrees, but I did a calculation for 6 degrees just to be conservative. And this is what we got. It's just trigonometry, the angle, and 25 kilometers the base. We just solved for the vertical component, which ended up 4,200 to 5,100 meters over the San Rafael Swell. Notice one thing here. The Green River Formation, which is probably a couple thousand feet thick, is one of the top formations to get eroded. That should make us think about whether the Green River Formation is from a post-flood lake or from the flood. Anyway, I'll let you think about that. So here's the total ocean sediments. All that material was eroded from the continents, ended up in the ocean, and I'm just going to pay attention to the thickness and where it is. So the continental margins, the average sediment thickness off the continent, just off the continent, maybe 50 miles width, is 3,044 meters, about 10,000 feet of sediment. This is average. And then there's a transition from the continental margin to the deep sea, and that was 2,189 meters, and the deep ocean has an average of 404 meters of sediment. So how much of that can we say ran off the continents during the retreating stage? This is what we concluded. All the margin sediments are from the flood runoff, because post-flood time, even including the Ice Age, wouldn't add hardly any sediments to that 3,000 meters of sediment along the margin. And we included all the sediments in the transition between the margin and the deep sea. But in the deep sea, we didn't have the foggiest idea how much of that was from the flood and how much of it is post-flood. I can give a case for a lot of sediments during the Ice Age and during the flood there. So we just split the middle and took 50% of the deep ocean sediments, which averaged 404 meters, and that was the amount of sediment. And then we placed all that sediment back up onto the continents to find out how much was eroded off. And it became 1,900 meters is our average erosion we calculated. That's about 6,000 feet. And the places I showed you were a lot more. So there's got to be places that had a lot less erosion, like the Midwest probably had a lot less erosions. But 1,900 meters, or about 6,000 feet, is the average runoff after day 150. And so to find the amount of sediments on the continents at the peak of the flood, you've got to add that to the amount that's on the continents right now. And that we've been working on, and we've been going state by state, because the states have their own geological surveys, and you can get a lot of data from the states. So before I get into that, I'm going to talk a little about what happened when the floodwaters were running off. For phase 4, when it was wide currents, I call it sheet erosion and deposition, because the currents were probably 1,000 miles wide and 5 miles deep. So when you look downstream, it has a consistency of a sheet, very thin and wide. So that was the flow of the currents and the deposition, phase 4. And in phase 4, you form these 5 features: planation surfaces. I've talked about this in some of my talks previously in geomorphology. And on my website, I got a whole ebook on the topic with color pictures. Planation surfaces, numerous erosional remnants like Devil's Tower, Monument Valley. Also, long transported hard rocks. In this area, they're quartzites, as a lot of you know. just east of Portland. They're down off the coast, near the Pacific coast. I find them in the Puget Sound area. They originated from northern central Idaho and extreme southwest Montana, or northwest Montana. And you find them 800 miles to the east-northeast into southwest Manitoba. So long transported hard rocks. Now other areas, you have a similar features, which I've gone into in a few other areas. And they're generally not quartzites. They can be chert, another hard quartz-like rock, and other hard lithologies. They form coastal escarpments and the continental margins, which I've gone into already. So that'd be phase 4. In phase 5, you have more channelized features that the erosion produced. Valleys and canyons rapidly. Water and wind gaps, like Grand Canyon's another water gap. Hell's Canyon is the deepest water gap in the United States, or actually North America, 8,000 feet high in northern Idaho. The Snake River should have continued out into Oregon if it was a slow process of erosion over millions of years like the secular scientists believe. But the Snake River takes a right-hand turn and goes through a mountain range up to 8,000 feet deep. We can explain that from the flood, but they have extreme difficulty. I've gone into all their hypotheses, and they're generally what I call in weather forecasting wild guesses. Also pediments and submarine canyons. So that's the project results of the continental margin sediments. And we've determined that the second result is that we've determined the sediments left for about 2/3 of the states in the United States using seismic and well data. We haven't done the western U.S. We've done Colorado and Wyoming. And the reason we haven't done the western U.S. is it's going to be hard because you've got so much tectonics here, up and down motions. You have huge basin sediments. You have a huge amount of volcanism. So it's going to be really hard. But we're going to do that in the future. So here's some of the average sediment thicknesses in some of the states. You can see some of them right there. There's just 7 there. The average is about 1,800 meters. I'm going to show you a picture below the sediments for Iowa. And you can see where the sediments lie there in Iowa, which is over 3,000 meters average thickness. So in order to progress on this project, we did a test state. By the way, all this has been published in the Creation Research Society Quarterly. We've had 6 papers we've published, and I just sent in the 7th one before I left. Like I said, John Reed does the heavy lifting. And in Colorado, it doesn't have many Precambrian rocks, which we had to evaluate. Where does the Precambrian fit into the flood? I'll get into that. That's controversial among flood geologists. But here's Colorado's map, lithological units. It's pretty messy. I'm just going to summarize things. The red are volcanic areas. The gray area are the continental crust that's been pushed up as the mountains, the Colorado Rockies. That's where the continental crust is. Now, to the east there, you see that big yellow area, that's the Denver Basin. And that the continental crust goes way down into that basin. Now, this red area down in here is the San Juan volcanic field. And we can't deal with volcanism. We're interested in sediments. So, in our estimates, we did not include the San Juan volcanic area, but we included some of the smaller volcanic areas you see in red. And we excluded the gray area because that is the continental crust already uplifted to 14,000 feet. And we started with Colorado because it has, like I said, very little Precambrian sediments, which we didn't want to deal with yet. So here's the volume and thickness for various basins in Colorado. And you see the average thickness is 1,900 meters, but if you averaged only where the sediments lie, it'd be 2,362 meters. And here's various basins you see here. The thickest sediments from the San Wash Basin in extreme northwest Colorado, over 5,000 meters. So when you plot it on a map, we had to white out the Colorado Rockies and the San Juan Volcanic Field. So this is where the continental crust lies. In the San Juan Volcanic Field, we don't know, but in the Rockies, it's way up there. In the Denver Basin to the east, it's below 10,000 feet below sea level. This is feet below sea level. And here's these basins in the western Colorado. This up here is the San Wash Basin, and the sediments go below 2,500 feet. We should have had a scale on here, but we don't. Anyway, you can see where the sediment collected, but this is a plot of where the upper crust rocks are. Sometimes upper crust rocks are up in the mountains. Sometimes they're way down in the basin that's filled up with sediments. So we had to determine, going to other states that have a lot of Precambrian sedimentary rocks and metasedimentary rocks, which are metamorphic sedimentary rocks, where can we place these? And this is a big controversy within creation flood geology. Do we put it in creation week, between creation and the flood, or the early flood? Those are the questions. And so I've determined it's in the early flood. Anyway, Precambrian is the area that has hardly any fossils. They have a lot of microfossils, by the way, and what's called stromatolites, which I'll mention a little later in the talk after the intermission. Anyway, here's the geological column, and with the names. The Precambrian is called the Proterozoic and the Archean, and that's older than 542 million years. And the boundary between the Proterozoic and the Archean is 2,500 million years. So it's this area down in here is called the Precambrian. How do they fit into the flood? And the first layer with fossils, a lot of fossils, is the Cambrian. You probably heard of the Cambrian explosion. Suddenly there was nothing in the Precambrian. Suddenly in the Cambrian you have representatives of all phylum that are alive today, and even a lot that have gone extinct. Suddenly in the Cambrian, called the Cambrian explosion, I call it the Cambrian Big Bang, because this is a strong evidence against evolution, because there's no ancestors there. It's part of the gaps in the fossil record. Here's my case for its early flood. The belt supergroup is from the flood. That is dated in the middle of the Proterozoic, and those sediments outcrop in western Montana, clear to Spokane, Washington. And that's where the quartzites come from, the belt supergroup. And that's so much sediment that it's hard for me to think that that can be between the creation and the flood. That and many other Precambrian features would indicate that catastrophism was so bad before the flood it destroyed the whole earth multiple times. Also, these big impacts we had during the Precambrian, the Vredefort and the Sudbury impacts, indicate that that'd be very difficult to place between creation and the flood, and even in the creation somehow. And they recently found this really surprising piece of data. Archean spherules over 2,500 million years old, the very lower part of the Precambrian, that indicate about 10 very large impacts early in the Precambrian. Ooh, that'd be kind of tough to put in the creation week, wouldn't it? And between creation and the flood. But so the only way we can fit it in Earth history, by the way, these are very solid results, thanks to the secular data. I keep up with 50 Earth Science journals, but I'm I look at what the data, the observations, and throw out their interpretations, and usually I can find a lot of good evidence for the flood. So because of all this, I've concluded that it's in the Precambrian. Let's take a look at some of this information. Here's the belt supergroup where it outcrops, and it's in the subsurface southeast of Glacier Park. And the amount of that sedimentary rock is 20 kilometers deep at the moment. But we know the top 5 kilometers or so got eroded. This is where the quartzite comes from, where, especially in the western part, the quartzites in the eastern part are not metamorphic rocks. They're hard cemented sandstone. There are 2 types of quartzite. But anyway, the quartzite comes from northern and central Idaho and extreme northwest Montana. Spread clear through into Saskatchewan to Manitoba and clear to Pacific Ocean. And quartzite, to form a metamorphic sandstone, you have to bury it and heat it up to maybe 200 degrees centigrade. So this implies that this whole belt supergroup rose up in the floodwaters, and the top was eroded off, top 5 kilometers or so, and spread the quartzites, which is the main resistant rocks in this area. The other rocks were soft and were pulverized. And is this belt supergroup? That's Precambrian. Another piece of evidence is that you have the Cambrian flathead sandstone, which is the same sandstone you find in the bottom of the Grand Canyon called the Tapeats, conformable on top, flat on it. My friend Peter Kleberg from Great Falls, Montana, has got his hand at the contact. So below, down in this area, is the belt supergroup, dated about 1.5 billion years, and the Cambrian limestone dated about 0.5 billion years, with a gap of 1 billion years missing, and there you got a flat contact, conformable. And the Cambrian, no one argues that that's early flood pre-flood, because that has a lot of fossils in it, and it just it means that the Precambrian and Cambrian were deposited with little or no erosion between them. It's a continuous sequence. So that tells me that the belt supergroup is from the flood. And here's the Redefort impact crater. The crater has you can see the rim, and it's got what's left. It's been eroded so much that you just see the central uplift of the middle is all that you have left. They estimate this crater was 250 kilometers in diameter, about twice the big as that Chicxulub impact on the Yucatan Peninsula that supposedly killed off all the dinosaurs. Anyway, here's what it looks like from space. You see the round, and that is from from the central uplift where it went up like that and froze like that, and then it got eroded like that. Here's the present surface. Here's the city of Johannesburg. So all this got eroded, and leaving these strongly vertical sedimentary rocks. They estimate the erosion here is 8 to 11 kilometers. All this that was eroded, 8 to 10 kilometers. Now that's going to be an important point as I get back to this and the Sudbury impact, where the sediments came from. So you have all these impacts very early in the flood. And what would they do early in the flood? Well, if they're as huge as the secular scientists think, namely Precambrian impacts. By the way, we find evidence for impacts within the fossiliferous sediment also. They estimate about 170 impacts that they have found. And by the way, they have very stringent criterion for determining an impact. And most of those criterion are so stringent that I think they missed probably 80% of them. Anyway, impacts will generate a huge amount of sediment. And when they hit the ocean, they're going to blast up all that water. And it's going to be spread up into the upper atmosphere and even beyond, but it's going to all come back down. It's going to spread out by the upper winds. There's where you can get your 40 days and 40 nights of rain from impacts hitting the ocean. They also cause powerful currents with great turbulence. Maybe currents going 300 miles an hour for a little while. It can explain what's called the Great Unconformity. How many have heard of the Great Unconformity? Yeah, quite a few of you. Anyway, you see it at the bottom of the Grand Canyon, but in my area, you mostly see it at the tops of the mountains, sometimes down in the valleys too. Also, a thing about the sedimentary rocks, maybe averaging 2,000 meters that are left on the continent, they're overwhelmingly fine-grained sediments, silt and sand. Now, if it's a slow process of erosion over millions of years, you should see a lot of conglomerates, but you don't. It's all been decreased down to small sizes. And it might even be able to account for the fossil order, but that's a project for the future. Anyway, getting back to that diagram, 1,900 meters is what we believe it was eroded off during the recessive or retreating stage. And what's left, we're finding out, is close to 2,000 meters. Maybe by the time we've done it, it might be 1,500 meters, but regardless, that'd be the ballpark estimate. So the total amount of sediment that you have to accumulate on the continents, on the average, is between 3,500 and 4,000 meters in 150 days. Generated in 150 days. Wow, that's a tall order. And it's deposited on the continents, but not in the present oceans. You got to have a powerful sediment generation mechanism and a powerful transport mechanism. We are looking for that in this project. What mechanisms did we have to form all those sediments? And they end up, 99% of them are fine grain, silt particles and sand, and some limestone, which are very fine. Limestone comes out of the water due to a change in temperature or change of other properties in the water. So that's what we're looking for, and I will tell you more about it after the intermission.
Thank you, Mike. Yes, very good.
Okay, let's see. Okay, the Precambrian rocks, I believe, are the Precambrian sedimentary, and sedimentary rocks have been metamorphosed, heated up, and changed, I believe, are from the early flood. And I've said that the Precambrian have a lot of microfossils, a lot of microorganisms in them, but hardly any macro organisms. But then there's something in there, especially in the Precambrian rock, they call stromatolites. And they're claimed to be biological and they take years to form. How many have heard of stromatolites? Not too many. Well, I'm going to show you some pictures. And then what I and others have discovered, stromatolites today, they're alive today, but they're very rare. They got to be certain types of water, and they're found especially in southwest Australia and the Bahamas, and they're found in some lakes. So they're very rare. Also, these stromatolites What they are, they're microorganisms that form a mat. And when current comes along and spreads particles of sediment, they collect that particles, and their mucus binds it. So it binds it, and then it forms another layer above it. So you have layer after layer of these microorganisms that bind the particles in the water that comes by them. And when you look at the ones today, they're very coarse-grained, and they bind all kinds of sediments. And the top are rough. They're very rough-looking, and they're kind of mostly, when they build up, they become kind of mushroom-shaped because along the bases of them, they get more eroded by currents. So there's a picture of some in the Bahamas. And here's the more famous picture in Shark Bay, Australia. Look how rough they are. They're kind of like the little mushrooms. They're only about a meter tall at the most. Mostly isolated. But then the ones you see they claim are in the rocks are a lot different than these. Oh, this is a cut through one of the stromatolites from that area you saw, that last area, from the Museum of the Rockies. So what are these things? We're talking about live microorganisms that bind sediments in the Precambrian, which I believe is early flood and a result of catastrophism. Well, stromatolites in the rocks are always found in carbonates. That's calcium carbonate that is dissolved in the water, and when the temperature of the water changes, or else you have chemical changes, the carbonates come out. They are deposited. So, and by the way, there's a lot of carbonate on the earth. 20 to 25% of sedimentary rocks are carbonates. You don't have a lot around here, but you go all through the Midwest there, and the Rocky Mountains, there's lots of carbonates. And also these layers I will show you pictures here soon. They're fine-grained, not coarse-grained. And they rarely separate into mushroom shape. Oops, I spelled that wrong. That was to wake everybody up. Okay. And sometimes you find them together in horizontal layers that you can trace for 100 miles. And they're sometimes in the mineral called dolomite. That's a carbonate, but it's calcium magnesium carbonate. Instead of all calcium, it's 50% calcium, 50% magnesium approximately. That's called dolomite. And when it says a rock, it's called dolostone. I conclude they're non-biological. How they were formed, don't know. And there's some secular scientists that don't believe these are biological either. Not too many. And there's some creation scientists who believe they're biological. So they have to say the Precambrian is a record of the pre-flood time, because they need the time. It takes time to build these layers up. But I think that they have a problem. Here is one in Glacier National Park. This photograph, they're white, actually. They're not blue. This photograph didn't turn out too well. But it's interesting. When you trace it to the right, maybe about 20 feet, this is what it looks like, just layered limestone. And by the way, they do claim that a lot of layered limestone is a stromatolite. Well, where's the bulbous nature of it, and or the mushroom shape and all that should be there? And then we found this is west of Libby, Montana, in the Belt Supergroup. These are stromatolites, most of the swirling of them, and they're continuous. These are in dolomite. Now, to deposit dolomite, calcium magnesium carbonate, you have to have temperatures of the water over 100 degrees centigrade, probably well over 100 degrees centigrade. And even if it was, some people think the dolomite was a replacement of calcium carbonate by adding magnesium ions into the calcium carbonate. That's pretty tough to do, but regardless, you still need temperatures over 100 degrees centigrade, whether it was deposited directly or it was replacement of calcium carbonate. So how are you going to have a live organism being deposited in water over 100 degrees centigrade? These are some of the features I find with the so-called stromatolites that they claim are in the rocks. So I don't believe they're biological. There's some special feature having to do with limestones and dolostone stones, and heat. One thing creation scientists are not recognizing is there's a lot of heat early in the flood. Dolomite being especially as a rock found in the Precambrian, by the way, indicating a lot of heat. Now, in our project, I'm going to show you some amazing maps of the upper crust. Remember, the upper crust is mainly granite rocks. Now, granite can be, that's not your countertops, by the way. They call them granite, but hardly any of those, if any, are really granite. They're metamorphic rocks. But granite, mostly granite, forms the upper crust. Below, into the lower crust, they're not quite sure what it is, but it might be a lot of basalt type minerals down there. And then once you get below the crust, you have the mantle for about 2,800 meters deep. Then you get to the core. Okay, this is in the upper Midwest. This is the Precambrian basement rocks below the sediments. And you see in North Dakota, up here, the Williston Basin, WB, and the surface of the Precambrian goes from 5,000 feet, this is feet below sea level, to 10,000 and probably down to near 15,000 feet below sea level. Notice how circular it is. I'm going to come back to that. Now this feature, this is a gigantic crack in the upper crust called the Mid-Continent Rift. This rift is 2,200 kilometers long. That's about 1,600 miles long from northeast Kansas through Iowa. Notice it goes through much of Iowa, up into Lake Superior, and then down and ends in Michigan. And there's other rifts down here, this yellow area. Remember, this is the Precambrian surface, and we mapped it below the rift. Now, secular scientists have not even done this. This rift, besides being about 1,500 miles long, is about 30 miles deep. These are in feet below sea level. Up there in Lake Superior area, 95,000 feet below sea level is what this crack used to be. And it's about 60 miles wide. This dwarfs Grand Canyon. Grand Canyon would be a little tiny thing in here. And yet this is in the upper crust. And you've probably driven over this area. Did you fall into a big crack? No, because it's been filled with sediment and volcanic rocks. About 50% sediments that are sedimentary rocks and 50% mostly basalt. So what in the world is this? How was this caused? We don't really know. We've got some educated guesses. But that's what we've discovered from this research project. A giant crack in northern Midwest below the surface. And here's what Iowa looks like, the Precambrian surface below the sedimentary rocks and feet below sea level. Like this contour is 2,500 feet below sea level right here. And look at how it goes way down there, maybe down to 50,000 feet below sea level. It's hard to, when we got so many contours in there, it's hard to see it. But that's what Iowa looks like, and that's why Iowa has an average of 3,243 meters which is over 10,000 feet thickness of sediment. And then here's your mid-continental rift going up here, and I'm emphasizing these basins. The Williston Basin, notice how circular that is, and it goes down to, here's minus 12,000 feet below sea level. Remember, this is the surface below the sediment. I believe the Williston Basin's an impact crater from a meteorite, maybe about 20 miles in diameter, that hit right here and formed this gigantic circular crater. I think the Michigan Basin over here is also the same, possibly the Illinois Basin and other basins are from impact craters. Here's a close-up of the Williston Basin as it goes way down to almost 15,000 feet below sea level, very circular. There's not too many things in geology that cause circular features on a large scale. In fact, there's only one, and that's meteorite impacts, where you have a huge rock coming from outer space that hits the land, and what it does is it blasts up and forms a crater. And then a lot of times the center will lift up and then sink again, and it can, what's called, freeze the rock. The rock becomes kind of like a liquid rock. You can freeze it with the central uplift that is still there, like I showed you in the Redfort impact crater, which I'll show another picture of that. Here's the Michigan Basin. I believe this is also an impact crater. It'd be about 300 kilometers in diameter. It'd take a rock about 20 miles in diameter, hitting about 15 kilometers a second. That'd do a lot of damage, wouldn't it? Now that's why I believe that these impacts are early flood. They started the flood. They created the huge chaos and turbulence of the flood and powerful currents. They couldn't be before the flood because these impacts, just the Redfort and the Sudbury impacts, which I'll talk a little more about, they can destroy the whole surface of the earth before the flood. I don't think it could have done it before the flood or in creation week. To me, the logical place to put it is in early flood. Early flood. And that has a lot of ramifications. Also, the great unconformity. That is what's called an erosion surface that you see in the bottom of Grand Canyon, you see in Montana and Wyoming, mostly at the tops of some of the mountains. And it goes down under into the Midwest below the sedimentary rocks and is exposed again in the Canadian Shield up there in eastern and part of central Canada as the Canadian Shield. And so this surface, I believe the only way you can form this is by powerful currents and turbulence that erodes down the land to a nearly flat surface. We call it a planation surface, but a lot of places it's not totally flat. Now this is Kansas. And because Kansas has so much oil, we were able to get thousands of oil wells. And when we mapped these things, we discovered that they had a lot of erosional remnants. Remember, this is the basement rock, the upper crust below the sediments of Kansas. Notice those tall, spiky things. I believe this one over here is a mistake, but these are about 800 feet tall, like Devil's Tower features sticking up. This implies that this surface, which is not flat anymore, it's been warped, that this surface was eroded quickly, because if a slow process of erosion over millions of years, you wouldn't have erosional remnants, because vertical faces erode a lot faster than horizontal surfaces. So you can't have any Devil's Towers or Monument Valleys on any surface that's been around for maybe only 100,000 years. Erosion should erode that a lot faster than down to the horizontal surface. This indicates rapid erosion of the great unconformity. Now this is a hugely messy chart. This is the upper crust of Wyoming. It's messy because in Wyoming you had powerful tectonics. The upper crust is probably flat at the peak of the flood over Wyoming. Then as Psalm 104 verses 6 to 9 say, the mountains rose, the valleys sank down. In Wyoming, that occurred on a massive scale where mountains went up and the sedimentary rocks on top of them got eroded off and deposited in the valleys. And the valleys went down. And the total length is 45,000 feet between the Wind River Mountains that are up to 14,000 feet, the top of the upper crust. This is this white area here, it's whited out, 14,000 feet, and there's a basin right here, Hanna Basin, that's down to 35,000 feet below sea level. That's why it's that green there. You see the scale here? That green, 35,000 feet below sea level. That's the max differential vertical tectonics, where the valleys sank, the mountains went up, Psalm 104:8, to drain the floodwaters. So, secular scientists and even a lot of theologians challenge us, well, how do you get the floodwaters up on the top of Mount Everest? Because there's marine fossils in that limestone at the top of Mount Everest. Well, that's pretty simple. All that area was below the floodwaters, and it came up. It all rose late in the flood. And I might add that all this tectonics is another name for just vertical or even horizontal motions. All this tectonics occurred in what's called the Cenozoic era in the geological column. Kind of late. That's exactly where we would expect it in the flood. Now I'm going to show you one thing here. These are the Wind River Mountains, the highest mountains in Wyoming. They're up to, with a number of peaks that are 14,000 feet. And many of those peaks are flat top because it's the top of the upper crust. But just to the southwest, we have the Greater Green River Basin, and you see a little green there, right next to the mountains. And this black area is so many contours that it turned black. You couldn't show contours. Like here's some contours you can see. And the green area is down to 35,000 feet below sea level. So you had the Wind River Mountains that were thrust up to 14,000 feet, and the Greater Green River Basin that was sucked down to 35,000 feet below sea level. That's what you had, which is kind of like this. Now that's powerful tectonics, and this happened at the peak of the flood to drain the floodwaters. So these are the features we're finding out. That map I showed you was from of the upper crust was from seismic and a lot of well data. So we're going to have to unpack this in the future to maybe show these features in smaller scale, because what's called the gradients of the heights are so great that the contours kind of mash together all together. Anyway, it becomes a mess. So these are some of our future goals. We're still working on these. Where did the sediments come from that ended up on North America, 3,500 to 4,000 meters thick? It's a work in progress. Well, this was published in 2022. This is the Southern Canadian Shield. You can see Hudson's Bay there. And these figures here are the amount of erosion the secular scientists believe occurred in the Southern Canadian Shield to form the Great Unconformity. Notice the numbers. The smallest number is 2 kilometers, and the largest is 11. So they believe in the Southern Canadian Shield, you had 2 to 11 kilometers of erosion at one time to form that nearly flat surface of the Canadian Shield called the Great Unconformity. There's where our sediments came from. They came from North America itself. It didn't come from the Pacific Ocean or the Atlantic, like I once thought. It came from the continent itself. And this is what John Reed had always been telling me, but I wanted to see some evidence, and this is it. The thickness of these rocks is based on the metamorphic rocks left on the surface. And metamorphic rocks take a certain amount of burial. That's how they get the depth. They might be exaggerating because they have to assume that the change in temperature with depth. But these are probably ballpark figures. Think of that, 2 to 11 kilometers of rock was eroded from this area. And not only from that area, but the great unconformity goes down under the sedimentary rocks we have out there today, down into northern Arizona. And this goes along with the Sudbury impact crater, where they eroded 5 kilometers of sediment, and Sudbury impact craters about right in here. They estimated 5 kilometers, so that we know that is a good figure. So that reinforces all this erosion of the Canadian Shield. And here's the Vredefort. This is 8 to 11 kilometers of erosion. See, when an impact hits, it forms a bowl-shaped feature. Vredefort is 250 kilometers in diameter. And when you blast off within seconds, 20 kilometers or 30 kilometers of the upper crustal rock blasted out and away, becomes unstable, and so the center wants to push up. It's called the central uplift. And in this case, the central uplift came in, it just froze there. And then you had 8 to 11 kilometers of erosion down to this surface right here, the present surface. A lot of action. And this is on another shield rock in Southeast Africa. So it's indicating that we had tremendous erosion right on the continents themselves that got pulverized this rock and sent it over the rest of the continent, didn't go out in the ocean, and was deposited and probably reworked back and forth. And here's what's called the North American Craton. This is supposed to be the stable area. Those numbers I showed you were right up in here. But the rest of the Canadian Shield goes up in here, and it's part of the great unconformity, and it goes underneath the sediments, which are through this area right in here. So that's where the rock came from. You have to erode that rock by some mechanism early in the flood. Now, we don't have too many potential mechanisms. Catastrophic plate tectonics, which from what I can see started in the middle of the flood, not early in the flood, because Pangea didn't split until mid-flood. And so you had a lot of activity before Pangea split. And that activity blasted all that rock away, formed small sediments, and redeposited on the continent. In fact, this is normally that brick pattern is normally the limestone pattern, but in this case it's sedimentary rocks. And the Canadian Shield has very few sedimentary rocks, but they have some in Hudson's Bay. So this indicates, and here's sedimentary rocks down in most of the United States. And the fact that you have some sedimentary remnants here is once you form the great unconformity, a huge planation surface, and the sediments spread away from there, some came back and covered the Canadian Shield. And then during the retreating stage of the flood, when the continent was coming up and water was running off, you eroded most of that sediment out. So I don't know if you caught all that, but it's a huge amount of activity that occurred early in the flood. Tremendous catastrophism. The more I study the flood, I just say, whoa, wow. And by the way, the Lord protected the ark. It says in Genesis 8:1, that God remembered Noah and the inhabitants. He didn't forget them. He just the word means he took care. He made sure they didn't get hit by a meteorite impact or come under on top of a volcano that erupted. So he kept the ark in deep water for when you had big tsunamis. In the deep ocean, it's just a gentle roller. Tsunamis are only a bit, when you get to shallow water, they're only a problem. So what do we deduced from this? 2 to 11 kilometers of rock eroded down to a planation surface. Whoa, that's a lot. In fact, a lot of us have been taught that the mountains before the flood were probably low. I mean, I believe this, but they could have been high before the flood also. But impacts can destroy all that, so it really doesn't matter how high the mountains are. And then once you erode that rock, the sediments are spread to other areas of North America. And then they're redeposited on the Great Unconformity. And later, during the retreating stage, they ran off and eroded most of that. A lot of activity, but that's what the geology of the area says. That's what it says. And it fits in really well with early flood. So what caused this catastrophism? A further clue, which I've been hinting at, is that practically all the sedimentary rocks are fine-grained. And CPT starts in the middle of the flood. And by the way, even if it started early in the flood, I don't think you can pulverize all that rock down to fine grain. See, it seems like the only mechanism is by impacts. Big rocks coming from space, 10 to maybe 50 kilometers in diameter, hitting the earth. You don't need too many that would destroy the earth. And that was the point of the flood. It says to destroy the surface of the earth. So it seems like impacts is about the only possibility that I can think of. And I've studied them for many years, and I got papers I've written. So now we're going to transition to our current study area. The Appalachians is very, very complex. Been a lot of ideas. Secular scientists got a huge literature. And they have a lot of contrary ideas. And what is difficult to explain is the Blue Ridge Mountains and the Piedmont to the east, which is an erosion surface, are highly metamorphosed. How did they get highly metamorphosed? Probably because they were buried deep and they came up from maybe the mid-crust. That's about all we can think of. So here's a picture of the Appalachians from space. They're very symmetrical with ridges and valleys. This is the Blue Ridge right in here, Blue Ridge Mountains. And this is called the Valley and Ridge. It's very large scale. It goes up into New England, but it becomes obscured. And it goes down into Alabama. And they map it into provinces. Number one is the coastal plain, which is sediment that was eroded off the Appalachians, forming the coastal plain and being deposited off in the ocean up to 18 kilometers thick. Number two is called the Piedmont. That's kind of a flat surface. A lot of metamorphic rocks. Number three is the Blue Ridge itself. Number four is the Valley and Ridge, which is just what it says, valleys and ridges. And by the way, at the peak of the flood, the valleys used to be ridges. And they got eroded down to where they're valleys now. A lot of interesting things happened in the flood. And number five is the plateaus. The Appalachian Plateau, that's in the north it's called the Allegheny Plateau, in the south it's called the Cumberland Plateau. And number six is interior low plateaus, which aren't really part of the Appalachians. That's the provinces of the Appalachians based on the surface features. And some of the sediments in the Appalachian basins go down to, I think, 30 or 35,000 feet. And you'll see, this is a messy diagram. It'd take you a while to digest it, but only remember this part, that to the right it's been crunched into valleys and ridges. Something has compressed it, or it's slid from off the Blue Ridge. But as you go further to the west, the sediments thin out over the plateaus. And then the coastal plain sediments is a thick layer of sediments eroded from the Appalachians out into the continental shelf and going down to down to 18 kilometers. Here's the cross section through the coastal plain sediments that thicken out towards the ocean. Some deductions on the Appalachians. The Blue Ridge and Piedmont, we believe, were overthrust northwest. They're pushed up. And we don't believe it's due to any continental collision. They have, this happened 3 to 4 times, they claim. And it was at a time in their model where there was no continent off the coast. So they have these terrains, they call them, that they come in and crash. But I think it's a pretty weak mechanism, and the evidence for it is not very impressive. So I don't believe that the pushing of the Blue Ridge and Piedmont up to the northwest was caused by any continental or terrain collisions. And then when you push up the Appalachians, you put pressure on the sediments, which are very thick in the Appalachian Basin to the east, and you cause it to thrust. So you caused the Blue Ridge and Piedmont thrust up, and it pushed up and put the force of compression to form the Valley Ridge province. It caused a sliding of the valley and ridge northwest and stopped at the Appalachian Plateau province, which are flat. Some deductions from all this. Now, on the Piedmont, there's all these rift valleys. See, the Piedmont is a metamorphic rock, but we have all these cracks in it called rifts. And they're filled with unmetamorphosed sediments with dinosaur tracks. And the whole area, after all this activity, was eroded 4 to 6 kilometers based on the rank of coal. So the eroded sediments that went toward the east formed the coastal plain sediments, which I showed you thicken towards the coast, and they become very thick offshore. And then sediments that went west ended up converging with sediments coming from off the Rocky Mountains and going south, filling up the Gulf of Mexico. It's all a consistent picture with the flood. And here are these rift basins in the Piedmont. Some of them are below the coastal plain sediments. That's the gray area you see there. Those are rift basins. We're especially studying this basin right here called the Deep Creek Basin. Now, some basins out here in the northern part of the Appalachians have 30 kilometers of sediment in them. And many of these basins have dinosaur tracks. I'll show you a picture of one of them from one of those basins. So the whole area was thrust up. And usually thrusts move on what's called a décollement, up like that, and you have multiple sheets of thrusts, as you see in this diagram here. This is similar to the thrusts that Peter Kleberg and I studied along the east slopes of the Rocky Mountains in Montana that you see from air. These are all thrust sheets right here. And the range from the mountaintops to the Sun River Canyon that goes through right in here, this is Gibson Reservoir, is 4,000 feet. So these things have been pushed up one after another. And notice to the west there's a valley with no thrust. And the Rocky Mountains are just to the left off the picture. So what we believe is that as the Rockies were coming up, it caused the sediments they call it gravity spreading, to go down and then push up. It's like a slump, a giant slump. and then you form all these thrust sheets, and then you have a hollow. And that's what this valley is here. I think this is the same thing that happened in the Appalachians to form the Valley and Ridge province that you see right in here, these ridges and valleys. And between the Blue Ridge Mountains and the Valley and Ridge province, you have what's called the Great Valley. In fact, it's continuous, goes up something like this all the way up. I think that can be similar to that trough that you see here, right in here, from the east slopes of the Rockies in Montana. And there's a dinosaur track you find in the unmetamorphosed rift sediment. Now, in the Deep Creek Basin, we're studying in North Carolina, they're about 10,000 feet deep. I think it's Connecticut, the Newark Basin is 30,000 feet of these sediments, all collected maybe in days, and dinosaur tracks on it, meaning that they're above the water for a while. So you had a lot of features going on in the flood. The flood was very complex. Anyway, here's a summary. 1,900 meters were eroded off the continent in the retreating stage. See, we're working our way backwards from the retreating stage going into the flooding stage. So roughly 2,000 meters left. I think that figure might be 1,500 to 2,000, somewhere in there. So that means about 4,000 meters collected by day 150. That's a lot of sediment, average on the continent, to be collected by day 150. The sediment originated from the continents themselves, and then got redeposited. And it implies great catastrophism, probably from meteorite impacts. Anyway, if you want to know more about this is some of the resources I have published over the years. This book, How Noah's Flood Shaped Our Earth, is about the chronology of the flood. How do we connect the chronology of the flood with the real world? We have a chapter on the pre-flood Earth. What do we know about the pre-flood Earth? Well, we have clues in coal, fossils, sedimentary rocks, and the Bible. And then early flood, what happened in early flood, late flood, and then what happened after the flood, caused by the flood, mainly the Ice Age. That's what that book's about. And this one I just published with Dr. Rob Carter, Biblical Geology 101. This is to educate the church on geology, basic geology, so that you can see these features of the flood out there for yourselves. You don't have to go to a lecture or read a book. Once you find out what's out there, see, there's a huge amount of evidence out there, but you gotta train your mind on what to see. And that's what this book is about. And of course, I couldn't leave the kids out. And this is good for adults too. We have a whole series of these coming out. This is the first one, Exploring Geology with Mr. Hibb. It's similar to Biblical Geology 101, but it's through the eyes of a cartoon character and very much simplified. We also have Exploring Dinosaurs with Mr. Hibb, and finishing up the last touches on Exploring the Ice Age with Mr. Hibb in the last couple of weeks. And this book, I wrote this book because I was at a pastor's conference, and a pastor came up to me and said, even your layman's book on dating methods and all that is too complex. So I made up my mind to write a resource for someone with no science background. And I was at a conference in Denver last week, and finally a layman came up to me and said, you made your goal. So that's what this book is about, going through all the dating systems with a lot of references for you that want to search out more details, called The Deep Time Deception. It has a subtitle called Examining the Case for Millions of Years. And I just published some books on the Ice Age. These are my most recent, published December. This is a summary of what I started with and various Ice Age projects through 50 years of research collected in this one resource, How Noah's Flood Caused a Single Ice Age. And in January this year, I published a layman's version on ice cores. I did a rather in-depth book with ICR, published about 20 years ago. This is a layman-friendly book, The Frozen Paradox, Ice Cores versus Deep Time. So that's all the advertisements, and now it's time for questions and answers, and I think we got a fair amount of time.
Yes, thank you very much, Michael.